Welcome to lesson 2.2, normal calculations. What is the standard normal distribution? This is denoted n parentheses mu comma sigma. It is a normal distribution that has been standardized. Therefore, all observations or data points or in units of the variable have been converted to z-scores, which means the number of standard deviations they are from the mean, and it's either above or below the mean. So if you have something denoted capital N parentheses 0 comma 1, then it means that it's already in a normal distribution that is standardized with a mean of 0 and a standard deviation of 1. What do we have to show when using the standard normal curve? Do 3 steps in each problem. 1, draw a picture and identify the values of interest. 2, show your work. And 3, answer the question in context. So find the proportion, which means the percent or the area, of observations from the standard normal distribution that are A, less than 0.54. Okay, so then if it's already the standard normal distribution, then we know that it goes negative 3, 2, 1, 0, 1, 2, 3, with 0 in the middle, because 0 standardized units from the mean, and then 1, 2, 3 standard deviations, or negative 1, negative 2, negative 3 standard deviations from the mean. Okay, and 0.54 means z equals 0.54. So if I just want to go from there to finding the area to the left of that, then I just need to go second distribution and go normal CDF, and my lower bound is negative 10,000, some really, really large negative number. My upper bound is 0.54. My mean is 0, and my standard deviation is 1. And then I get 0.705. Okay. All right. And then greater than negative 1.2, I'm going to go second distribution, normal CDF. Lower is negative 1.2. Upper is 10,000, some really, really large number, mean of 0 and a standard deviation of 1 because it's on a normal curve with a mean of 0 and standard deviation size 1 because it just counts from ones. Okay, and then I hit paste and I get 0.8849. Okay, that's pretty close. Did I do that wrong? Okay, I think negative 0, negative 1.12, yeah. Oh, okay, slightly different, sorry about that. Second distribution, normal CDF, negative 1.12. Okay, 0.8686. All right, so also, when I'm finding the area greater, it's also 1 minus the area less. And so let me show you why that's an important distinction, because you can also use a table to find these areas. Now, the table always finds left areas. So if you're looking for an area to the right of negative 1.12, then you're going to use the table like this. Negative 1.12 is here, and that area's 0.1314 is the area to the left of that cutoff. But this asks for the area greater than negative 1.12, so the right-hand side. So to get the right-hand side, we know that the whole curve is an area of 1, just by definition of density curves. We know if the left side is 0.1314, then I can take 1 minus that left white area to find the right shaded area, 0.8686. Okay, greater than 3.49. So remember that the tables are always left-sided, and 3.49 is right here, 3.49. The left area is 0.9998. This question was looking for the area greater, so it'd be 1 minus 0.9998, or on the calculator, second distribution, normal CDF, the lower bound is 3.49, the upper bound is 10,000, mean of 0 and standard deviation of 1, and it's basically 0.0002 Okay, so that's the same as this. All right, between 0.49 and 1.82, I find this is easiest on the calculator because I can make that lower bound specifically 0.49, sorry, 0.49, and the upper bound 1.82, and then mean of 0 and standard deviation of 1.2777, okay? But on the paper, if I want to find this left bound, on the table, if I want to find this in-between area, I actually have to find the left bound, okay, the entire left bound from 1.82, and then subtract from it the left bound of 0.049. And that's just kind of like finding the area of a shaded region back in geometry class. You would say like, oh, I have a box, but I just want to find this shaded region here. So then you'd say, okay, well, take base times height and then minus the white triangle, okay? And then you'd find just the shaded region. So now, if I have a shaded region that's like this, I'm gonna have to act like I have the whole shaded region that I can find, because I can get that value from the table, the whole shaded region, and then go back and subtract from it that shaded region. Okay? And then you're left with the in-between shaded region. So we start with the larger shaded region, so the further right value, 1.82, and then we subtract from it the 0.049. So that works like this. 1.82 has a left area of 0.9656, and then 0.049, the white area that I want to subtract from it, has a left area of 0.6879, and then we get 0.2777. Find the area within 1.5 standard deviations of the mean. The area from negative 1.5 to 1.5. So we're going to go from negative 1.5 to 1.5 and find this inside area. Okay. All right, so first I want to go the area to the left of the positive 1.5 so I can get this whole cumulative left area. Then I want to subtract from it this little white area, so I'm left with that shaded region in the middle. Okay, so 0.9332 is the whole thing, well, everything left of this border, and then 0.0668 is everything left of the other one, because it's a symmetrical distribution, so it's kind of like one minus the other, but either way. Okay, so 0.9332, and then 0.0668 is 0.8664. A distribution of test scores is approximately normally distributed. Joe's scores in the 85th percentile. How many standard deviations above the mean did he score? So, starting inside the table, find the area closest to 0.8500. Alrighty. 84, 86, 85, right in between these two. And it's closer to this one. So we're just going to go with whichever one it's closest to. Since this one is 0.0015 away and this is 0.0008 away, 0.0008 is smaller than 0.0015, so it's closer to 0.8508. So it'd be 1.04 is the z-score. Okay, so he is 1.04 standard deviations above the mean test score. In a normal distribution, Q1 is how many standard deviations below the mean? Q1 is a 25th percentile. Look inside the table for 0.2500. Okay. Okay, 0.2514 is closer. That was hard for me to think. Okay, so then negative 0.67 is the closest there. Okay, right there. All right, so Q1 is 0.67 standard deviations below the mean. How long is the IQR in terms of standard deviation? From Q1 to Q3, we can use the answer from before. If Q1 is negative 0.67, then Q3, the 0.75 mark, must be at positive 0.67. So since the normal curve is symmetrical and Q1 has a z-score of negative 0.67, then Q3 has a z-score of positive 0.67. So 0.67 plus 0.67 is 1.34. The IQR is 1.34 standard deviations long. According to the CDC, the heights of 12-year-old males are approximately normally distributed with a mean of 149 centimeters and a standard deviation of 9 centimeters. What percent of 12-year-old males are less than 160 centimeters tall? Draw a picture, talk about how to use. Okay, so when we draw this out, we realize that 160 centimeters is kind of that, I think it's the same question that we came up with before as just a motivator for this lesson when we were doing the empirical lesson. So 160 is not one of the standard deviation values, like 1, 2, or 3 standard deviations away from the mean. So we have to use the z-score formula to turn it into a z-score and then use a table or the calculator to turn it into a area. Okay, so his height to z to area. Okay, so observation minus the mean over the standard deviation is what's going to turn this into a z-score. So we put this unique individual of 160 centimeters tall minus the mean of 149 divided by 9 is 1.22. So his standard deviation is 1.22. And we find the whole area left of 1.22 of a z-score of 1.22, and that's 0.8888. So that can be found again going second distribution. Oops. Normal CDF, the lower bound is 10,000, the upper bound is 1.22, and we get 0.8888. Okay. So he's approximately in the 88.9% of boys have an area less than him. What percent of 12-year-old males are greater than 145 centimeters tall? So 145 centimeters is right here. And we're looking for this dashed area. 145 minus 149 over 9. Notice the formula is just the same as before because it still has the same mean and standard deviation. I'm talking about the same distribution. Okay, is negative 0.444. And we're looking for the probability of any z value being greater than negative 0.444. And that's 0.67. So we're doing a right-handed area, so second distribution. Normal CDF, 0.444. Negative 0.444. Okay, and upper is a really large number so that we can get the whole right-hand tail. Okay, and then 0 and 1 because I'm talking about a normal distribution because this is a standardized value because it's already a z-score. Okay, and we get 0.67. What percent of 12-year-old males are greater than 190 centimeters tall? 190 is way out there, so let's try to figure it out. Probably that x is greater than 190 is a probability that z is greater than 190's z-score, and that's 4.56. That's extremely high for a z-score. And that is essentially a really small number. So let's go ahead and just show that in the calculator. Second distribution, normal CDF. 4.56 is the lower bound. The upper bound is 10,000. Mean of 0, standard deviation of 1. And it is 0.000002. Okay. What percent of 12-year-old males are between 140 and 160 centimeters tall? Okay, 140 and 160, and we found 160 earlier. And then we still need to find 140. So we can say that 140 is 1 standard deviation to the left, so you can jump right to here then and say that's from negative 1 to positive 1.22. Okay. And if you're going to find that area in between, remember how to do that. We are going to find the cumulative left area, so find the area to the left of the larger number. Probability that z is less than 1.22, and then subtract it from the left area over here to get rid of that white unshaded region, and that's 0.888, that number. minus this new number, 0.1587, and that is 0.7301. What is the 85th percentile for heights of 12-year-old males? Okay, so we want to find the 85th percentile, so we don't know what cutoff this is. Okay, so I just did this like little dash line thing and question marks. Look for 0.8500 in the center of the table. So now you should be feeling a little bit of repetition of going over these problem types. I'm going back to the center of the table and I'm looking for 0.85. So it'd be somewhere greater than 0.5, and this whole page is all the positive z values. That means it's all the z's to the right of the mean. And if I'm looking for an 85% cumulative left value, then that has to be to the right of the mean. 0.85 is right here. I feel like I already did that one once today already. That's okay. Okay, and that's a z value of 1.04. Okay. I lost my place. Okay, very good. Z value of 1.04, and then I think that's good there. Yeah. What is the value of Q1 for 12-year-old males? Look for the 25th percentile. Already did it once before. Negative 0.674 was that Z value. Looks like we did something really similar over here. Okay, and then we set it up like this. Z equals observation minus the mean over the standard deviation. We already did a problem like this in the notes too once before. Okay, multiply by standard deviation, add the 149 over, and get 142.93 centimeters tall. That's the height of a person in the 25th percentile. In the 2008 Wimbledon tennis tournament, Rafael Nadal averaged 115 miles per hour on his first serves. Assume that the distribution of his first serve speed is approximately normal with a mean of 115 and a standard deviation of 6. Okay, so remember to do 3 steps on each problem. Show your work, okay, draw your picture, and then you should answer in the context. About what proportion of his serves would you expect to be slower than 103 miles an hour? So we're looking for a left area. I need to see 2 things then. I need to see your left inequality, okay, less than, and I need to see your left shaded region. I need to also see the z-score in your work, and then the final area, okay? You don't have to answer in a sentence format, answer in the context, unless it asks you to describe what this means, okay? About what proportion of his first serves would you expect to exceed 120 miles an hour? So we find 120, draw a new distribution, find 120, shade to the right, and then for exceeding 120 miles an hour, and then I have the right shading and the inequality, okay, showing that I'm looking for observations greater than 120. Show your work to find your z value. Make sure you explicitly show your work and give the z value. Then move on to finding the area. Okay. So what percent of Rafael Nadal's first serves are between 100 and 110 miles per hour? So now I'm looking for an area between. This should start to feel a bit repetitive. I did a left area, a right area, now an area between. So we look for the probability that some observation is between 100 and 110. That's the same as the probability that some z value is between the z-score for 100 and 110. Z-score for 100 is negative 2.5. Z-score for 110 is negative 0.83, because both these values are less than his mean number of miles per hour for his serve, 115. Okay, so we find the rightmost left area first, then the left side left area. So we take the 0.2023 minus this little white unshaded region, 0.0062, and we get 0.1961. We found those regions by first looking at that more right area, the negative 0.833, .2033, And we also found the negative 2.5. And that's 0.0062. And I must have used my calculator to find this area because it's a little bit more specific because I had all those decimal places. And that's how I got that value. The fastest 30% of Nadal's first serves go at least what speed? So I know I want some upper 30% cutoff. Okay. That means that I look for actually 70% in the table's center, because remember that the table reports left areas. So I'm going to look for that z-score that cuts off 70% to the left. So I'm looking for a 0.70. Okay, that's the closest one, 0.52. So, and in my calculator, I found it's 0.5244. And I'm going to solve for the observation minus the mean over the standard deviation equals 0.5244 times by 6, add 115, and you get 118.15. That means that 30% of his serves go 118.15 miles per hour or faster. So what can I do on the calculator? Second distribution, inverse normal. You have an area of 0.70, and your calculator is always going to find left areas as well, just like your table does. Okay, so instead of typing in 0.30, make sure that you convert it and you type in 0.70. So second distribution isn't that smart when it comes to inverse normal. It just asks you for an area. It doesn't tell you left area or right area or any of that, like lower bound, upper bound stuff. So 0.70 goes in here, okay, meaning I'm looking for the left area of 70%. That gives me the same z-score at the bottom here where that caret is, that cuts off the upper 30%, okay, and that was 0.5244. Okay. A different player has a standard deviation of 8 miles per hour in his first serve, and 20% of his serves go longer than 100 miles an hour. If the distribution of his serve speed is approximately normal, what is the average first serve speed? So I know the standard deviation is 8, I know the mean is 100, and I know that z equals negative 0.84, okay? And that's because that's the 20% z-score. So inverse normal, the area is 0.2, and that gives me the left area's z value, okay, negative 0.84. And then I pop it in here and I find the mean, 106.72. Oh, I'm sorry. I called that the mean earlier. That's his unique serve cutoff that we're talking about. Okay. How do you do normal calculations on the calculator? Okay, so here is a little technology corner for you to work through in case you wanted to see that explicitly worked out slowly. Press second distribution, normal CDF, lower, upper, mean, standard deviation are the values that go in the parentheses. We use something like 10,000 or negative 10,000 if the boundary is unbounded. Second distribution, inverse normal, in order to go the other way from area to a z value. Okay. So what do we need to show on the AP exam? You need to always show the problem setup with an inequality less than or greater than. You need to always show your picture, your work with the z-score, okay, and then your final answer in area. Suppose that Clayton Kershaw of the Los Angeles Dodgers throws his fastball with a mean velocity of 94 miles per hour and a standard deviation of 2 miles per hour, and that the distribution of his fastball speeds can be modeled by a normal distribution. About what proportion of his fastballs will travel at least 100 miles an hour? So I have a little tiny area over here, so I need to make sure that I draw that area out, and that I also think that in the end I need to get a really small area. In this case, I'm going from context to Z to area. That's the most typical way to go. Okay, when you go from context to Z, you show work. When you go from Z to area, it's just a table or a calculator. Okay? All right, so Z equals 100 minus 94 divided by 2, which is 3. Then we have a Z-score of 3, which made sense because 100 was exactly the cutoff for the 3 standard deviations to the right. And we're looking for the probability that Z is greater than 3, which is 0.0013. About what proportion of his fastballs will travel greater than 100 miles an hour? Okay, so the distinction here is that the first one was at least 100 miles an hour, so that means 100 miles an hour or greater, and this is greater than 100 miles an hour. Well, probability that Z is greater than 3 is equal to 0.0013 because there's no area in the normal curve directly above a single observation. So the probability of x equaling 100 is 0. So the probability that Z is greater than or equal to 3 is also equal to the probability that Z is just greater than 3, which is the 0.0013 number. About what proportion of his fastballs travel less than 90 miles an hour? 90 miles an hour is exactly 2 standard deviations less than the mean, so we can just count that out, use probability that Z is less than or equal to -2. I don't have to show that work there because it's actually just exactly 2 standard deviations to the left. And I get 0.02 for the area to the left, or less than 2 standard deviations to the left. Oh, 2 standard deviations, yeah, to the left. About what proportion of his fastballs will travel between 93 and 95 miles an hour? From 93 to 95 miles per hour, I no longer have that shortcut where I'm right on a standard deviation marker. Okay, so now I have to go all algebra. Probability from 93 to 95 is the Z-score for 93 and the Z-score of 95, taking the upper area minus the lower area and getting the difference. About 0.38 of Kershaw's fastballs travel between 93 and 95 miles per hour. What is the 30th percentile of Kershaw's distribution of fastball velocities? Okay, so I want to know this area, 30%, what is the fastball speed? So I'm going to go inverse normal, area of 0.30, mean of 94, standard deviation of 2, and I get 92.95. These things should start to really feel like we're repeating ourselves over and over because I just found tons and tons of examples of doing these types of problems. Okay, what fastball velocities would be considered low outliers for Kershaw? So outliers is 1.5 times IQR below Q1 or above Q3. So I'm going to take that and I'm going to work that out here, and I'm going to find that observation that is at least that much lower than the Q1 and at least that much lower than Q3. I find that the IQR is 2.7. So 1.5 times IQR is 4.05. Okay, so then I'm going to subtract that from Q1 and I'm going to add it to Q3, and I'm going to get that anything slower than 88 miles per hour is a low outlier, and that I must be finding the other one here too. It looks like I found the Q1 and the Q3 by using negative 0.67 and 0.67. Okay, Q1 Z value is negative 0.67, Q3 Z value is positive 0.67. Okay. Oh, just low outliers, sorry. I read low or high outliers in my head. Okay, so that's it. So just looking for anything that would cut off the low outliers. Okay, very good. Suppose that a different pitcher's fastballs have a mean velocity of 92 miles per hour and 40% of his fastballs go less than 90 miles an hour. What is the standard deviation of fastball velocities, assuming the distribution of velocities can be modeled by a normal distribution? So one thing that I know is that the mean velocity is 92. The area of 0.40 has a z value of negative 0.25335. Okay. And that at that observation, that is a 90 mile an hour fastball. Okay, so what is the standard deviation? So I'm going to put in all those parts that I know. The z value at 90 is negative 0.25335 because it's the 40th percentile cutoff. And then 92 is the mean, and then standard deviation right there. So you multiply both sides by standard deviation, divide by negative 0.25335, and I get 7.89 miles per hour as a standard deviation. The weights of a 9-ounce bags of a particular brand of potato chips can be modeled by a normal distribution, with mean 9.12 ounces and standard deviation 0.05 ounces. What proportion of bags will be underweight, therefore less than 9 ounces? So 9 minus 0.912 divided by 0.05 is negative 2.4. Then what bags are going to be less than 2.4? Probability of bags less than 2.4 is 0.007. A proportion of 0.008. A proportion of 0.008 chip bags are underweight. What proportion of bags will weigh between 9 and 9.25 ounces? Between 9 and 9.25 ounces is gives you the z-scores of negative 2.4 to 2.6, and we would subtract the upper area minus the lower area, so 0.9953 minus 0.0082, about a proportion of 0.987 chip bags are between 9 and 9.25 ounces. What is the 40th percentile for bag weights? Inverse normal, area, mean, standard deviation gives you negative 0.2533. All right, so then we work this out. Z equals observation minus the mean over the standard deviation. Start to solve, and you get 9.107. About 40% of bags weigh less than 9.107 ounces. What weights would be considered low outliers for these bags of chips? Q3 is a 75% area, Q1 is a 25% area, and we need to use both of those and turn those into context, into bags of chips. So I'm going to use this shortcut: inverse normal, area, mean, and standard deviation of this context, 0.912, 0.005, 0.05, and I get 9.154 ounces is my Q3, 9.086 ounces is my Q1, and I need to subtract Q3 minus Q1 and times it by 1.5, and I get 0.102. Okay, so that is 1.5 times IQR, 0.102. Okay, and I need to take Q1 minus that amount, and then I'm finding the value that is 1.5 times IQR less than Q1, and that is my boundary for anything that is an outlier. That would be all the bags that weigh less than 8.984 ounces. In the United States, egg sizes are set by the Department of Agriculture. A large egg, for example, weighs between 57 and 64 grams. Suppose the weights of eggs produced by hens owned by a particular farmer are normally distributed with a mean of 55.8 grams. If 20% of eggs from these hens are extra large, greater than 64 grams, with a standard deviation of weights, what is the standard deviation of weights and eggs from these hens? So the mean is 55.8 grams. The z-score is 0.842 because we are looking for the 20% mark. So we're kind of, in a way, we're given an area, we're in a way given a z value. I mean, sure, we have to look it up, but the area gives us that z value right there. And then it's 64 grams, that is the upper 20% cutoff. So we got the z value then we can plug it in. Z equals the observation minus the mean over the standard deviation. Based on your answer from part A, what percent of eggs from these hens are large? What percent of eggs are between 57 and 64 grams? So do 57, do 64 through a z-score conversion, get 0.12 to 0.84. So only that shaded area is this type of hen's large eggs. 25%. About 25.11% of eggs laid by these hens are considered large eggs. So the things that are required of you: draw it out, show all of the values 1, 2, and 3 standard deviations above and below the mean, show your inequalities. This is a compound inequality. Show your work for each component, show the actual z values, shade it, and get up to your final answer in area and write it in a sentence. Assessing normality. This is a little bit fuzzy right now. What I would do for assessing normality is first try to look at the shape and see if it's reasonable to assume that the distribution could be normal. And then I would also try to back it up numerically. Try to use your empirical rule, 68, 95, 99.7, and try to confirm that the data, 68% of the data is within 1 standard deviation, 95% is within 2 standard deviations, and 99.7% of the data is within 3 standard deviations. Obviously, you won't get exactly these percentages, but you get something close. So you'll be able to say it's reasonable to assume that the data is normally distributed. So we need to check for normality using table A or normal CDF to convert from z-scores to percentiles and vice versa. The measurements listed below describe the usable capacity in cubic feet for a sample of 36 side-by-side refrigerators. So these are all the capacities of the 36 refrigerators. I wrote a key. I looked at it. I thought that looked really reasonable to assume that the distribution is approximately normally distributed. I found a mean and a median. I found a standard deviation, and I started counting. Mean plus 1 standard deviation, 2, and 3 standard deviations give me these regions. And then if I count the refrigerators that are within those intervals of values, I got 66%, 95 approximately percent, 94%, and 100%, which is so darn close to 68%, 95%, and 99.7%. The percent of observations within 1, 2, and 3 standard deviations of the mean is very close to 68, 95, and 99.7. Assume the distribution is approximately normally distributed. We can also create a normal probability plot. This is even better, to determine whether a distribution is approximately normally distributed. When looking at a normal probability plot, how can we determine if a distribution is approximately normal? Look for a roughly straight line. So AP exam tip, normal probability plots are not included on the AP topic outline. However, these graphs are very useful for assessing normality. You may use them on the AP exam if you wish. Just be sure that you know what you're looking for, which is a linear pattern. Here's my data entered in my L1, and what I'm going to do is I'm going to go second stat plot, and I'm going to turn plot 1 on. And I'm going to go down to, or over to the last example of a plot. It really just looks like a straight line, but it is a normal probability plot. It's pulling from my L1 because that's where I put my data, and I want my data axis on the x-axis, on the horizontal axis, and then it'll put my z-scores on the y's. So what it's actually doing is go second quit, go zoom stat, which is zoom 9. Okay. What it's doing is it's graphing each point as an ordered pair, as a scatter plot, and it's graphing each point with its z-score. So this is just the straight x-axis, and this goes from, let's just say 12 to 19, counting by ones. Okay. So that is 12, 13, 14, 15, about 16, 17, 18, 19, and this is the z-values, -3, -2, -1, 0, 1, 2, 3. Now, so we see that values of about 16.0 have a z-score of 0, okay? And so therefore we're kind of seeing that about 16.0 is the mean, 15.8. Okay, pretty close though. So what we see here then is that we have a really straight line, and that's wonderful. And we also see a bigger clump of data around the middle, and fewer on the edges. That kind of mimics that normal curve of the hump in the middle and the tails on the ends. Okay? Also, what it's doing for us is, because of the straight lineness, we know that there's not a whole bunch of skew. Okay, if we had a skewed graph, then the normal probability curve, maybe it'll go something like this or something like this. Okay, so here's an example of a histogram with a normal probability plot comparing with it, and we do see the skewness, and we see that skewness right here, where these extreme values are still within the second standard deviation, okay, away from the mean, but they are actually pretty extreme on the x-axis. And then we see the majority of points is a little bit to the left here on the x-axis. And then we see this sharp drop-off in points right here. Okay, so I kind of see the tail. Okay, and then I see the mass of points. And then I see the drop-off. Okay. All right. So that is kind of the skewed graph explained on the normal probability plot.